Hello, students. We're going to continue our discussion of reaction mechanisms. In the previous video lecture, I introduced the concept by doing a problem that we had already worked out the rate law for from methods of initial rate. Just to recap some key important ideas, and then we'll do another example. As a mechanism, it's the play-by-play behind the scenes of what is happening on a molecular level, which molecules are colliding with which molecules. Most reactions happen in multi-step mechanisms. And this is not something we look at the balanced equation and say, oh, this is the mechanism. Mechanisms take a long time to develop, and they have to be proven experimentally. So the way they're proven is through the kinetics data, and the rate law expressions have to match. Okay, so the individual steps of the mechanism are called elementary steps because they describe a single molecular event. And each elementary step is characterized by how many particles are involved in the reaction, which is known as molecularity. So let's take a look at this little chart. So if you have an elementary step, just one reactant to product, that's unimolecular, and that is unimolecular. That's going to mean that if you double A, the rate doubles, because that's exactly showing us the exact process on a molecular level on how they're colliding. So in that case, the reaction rate would be first order. And I think that that's missing a little K on there, so I'm going to put that in. So first order. So unimolecular is always first order. If you have two molecules colliding, that's bimolecular, that's always second order. If you have two molecules that are different, that's also bimolecular, and that's overall second order. Okay, stopping here for a second. If I double A, the rate will double, so that's first order for A. If I double B, then that's first order for B. Okay, so elementary steps allow us to determine the rate law from them. This is not true of an overall reaction because the overall reaction is not showing who exactly is colliding with who to make product. The last one shown here is a termolecular. This is highly unusual in a mechanism because the statistical analysis of how likely it is for three molecules to collide in the correct orientation is very improbable, very low. So termolecular is extremely unusual in a mechanism. So they're usually unimolecular or bimolecular. Okay, so to recap from the previous video, the NO and CO collide to make NO and CO2. The proposed mechanism was here, two steps. And what I want you to think about here is that you cannot come up with these mechanisms. This is given. What we were given was that or can be given is that this step here, the first one is slow. And in this mechanism, the second one is fast. That would also, as written here, was given. The rate determining step is always, always the slow step. And we can therefore say that for this first one, rate equals K NO2 squared because it's bimolecular and it's the same reactant. And that if this is a valid mechanism, that rate will match the experimental. Okay, so let's practice another one. We did that one in the previous video. I already said this, so I'm going to skip. Okay, so let's try this one. Take a moment and pause this slide. What I'd like you to do is to write the overall equation from the two steps. We have step 1 in step 2, confirm that when you add them, you get the overall equation. Determine the intermediates. Determine if it's unimolecular or bimolecular. And then the last thing I want you to do is write the rate for the slow step. Okay, so pause me and do all that. Okay, so I asked you to do the following. I asked you to confirm that added together, you get this overall reaction. So 2NO2 plus F2 makes 2 of the products. You have 1 and 2, so we're adding the equations. You have 1 and F2, and then you have 1 and 2 NO2, right? Okay, and then the F is the intermediate. It's formed, but it's immediately consumed, so it's not part of the overall equation. Okay, the first step has 2 molecules colliding, so that's bimolecular. And the second step is also bimolecular. And then the slow step is the rate determining step. You can't go faster than your slowest step. So in this case then, we're going to write the rate law for the slow step. Rate will equal K times NO2 times F2. So I'm pulling that from the balanced equation. I can do that only on elementary steps. And now I look to see, does it match the experimental rate law? And it does. So yes, this is a valid mechanism. Okay, and that's really all that we're getting the feel for here. And one other thing to consider is that the slow step then most likely has the higher activation energy, right? So our slow step has a very high activation energy compared to the fast step. That's why it's bogging down our process and our rate law. Okay. This one here is our last one that we'll go through. This one's a little bit different. It's a little more intimidating, but this one is different. Multi-step process. So the first parts get a lot easier, right? So we can add those up. NO3 is our intermediate. It's formed and then consumed. And then we end up with 2 NOs plus O2 make 2 NO2s. And that's our overall reaction. So we're good. What's different here is that the fast step is the initial step. So the slow step still doesn't matter. The slow step still determines how fast the reaction happens. So I'm going to write down rate equals K times NO3 times NO. I go to C, okay, done. But then I have a problem that they don't match. This doesn't match the experimental rate law. This does not mean it's wrong. So there's something else here at play that we have to fix this. And so the NO3 here, I'm going to highlight it. The NO3 is in the in the elementary steps rate, but yet it's not part of the original reaction, right? That's an intermediate. So what we have to do is we have to, I guess you'd say, get rid of it. We have to convert or express the concentration of NO3 in terms of reactants. And the only way I'm going to be able to do that is to go back up to my fast step. The way I'm going to do this is I go back to the fast step that precedes it, and I'm going to say, okay, the rate of the fast step is K times NO times O2. That still doesn't help us because that doesn't have NO3. And here's the part that I think is kind of hard at first for students is that this reaction being fast has double arrows. You see the double arrows, it means it's reversible. We're going to talk more about reversible reactions in the next chapter. So I'm just going to introduce it here. And that is that when they're reversible, they reach an equilibrium where the rate going forward equals the rate going reverse. So I'm going to show this rate with a little f. Down here, it shows it as K1 if you want to follow the typed out part. But now the rate going forward equals the rate going reverse. So I'm going to call that K reverse. And that's going to be in terms of NO3. So if I'm thinking of this one here going backwards, that would be the rate law for that elementary process. And now what I'm going to do is now maybe you can see where I can do some algebra because here's NO3 concentration. And so I can make a substitution. So I'm going to switch colors. You're going to substitute. Oops, I did not want to use that one. Okay, I think I'm not going to switch colors. We're going to do a substitution. Do you see how NO3 equals, I'm going to write it here, rate equals that, which equals KF over KR equals NO times O2. That equals NO3. And that's what I'm going to substitute into here. Okay, so I'm going to try to get fancy and keep this NO3 in the green so you can see the substitution, and then keep the other one in purple. So rate equals K for the second reaction times NO3, that's going to be this green one here, all that. Okay, that's just the substitution. And then all that is still, okay, I substituted it, but I still have this NO. Okay, so this is a substitution. And then now I can clean this up. I have a bunch of little k's. And the thing with constants is that you can make them into a new constant. So what will eventually happen here is I'm going to have my rate times K for the overall process. Do you see how NO times NO is NO squared times O2? And now that matches. Experimental rate law. So this was a valid mechanism. It just didn't look like it at the beginning. Okay, so recapping, the mechanisms, the slow step is always the rate determining step. That's going to determine how fast your reaction goes. If the slow step is second, you write your slow step rate. It's going to have an intermediate in it. So you're going to have to go back up to the fast step and solve for concentration of intermediate using that reversible reaction. Now, what I think can really help, and it's officially not the way to do these, but if you want to just make it easier on yourself, let me do this. Like, these little K's kind of throw a lot of issues in, right? So if I just ignore those guys, do you see how the concentration of NO3 equals concentration of NO times O2? Just substitute it. And don't even worry about the little K's, because you know that ultimately you have a K there. And so I think if I do that, get rid of all the little K's, it's just so much easier to see what we're up to. And we're just substituting. We're substituting the intermediate with the reactant concentrations. Okay, so now at this point, I would go and practice some of the assigned homework for mechanisms and see the kinds of questions it asks. It'll ask things like, is it bimolecular, unimolecular for elementary steps? What's your intermediate? Why is the slow step important? It'll ask you, what's the overall rate law if this is the slow step? So it's not quite as difficult as it seems. So practice some, and then if you have questions, let me know.